Hello, everyone. Just a quick recap of what we did last week. Last week, we made mention of the chain rule, but we mentioned that one thing that's so foundational to the concept of the chain rule is the composite function. And we said that the composite function is made up of two or more functions in which the output of one function become the input of the other. And that is so important. But today we are looking at the higher order derivatives. All right. So consider the function y equal to f of x equal to x to the power 4 minus, let's say, 2x to the power cube plus 1. Now, the its derivative, okay, would then be what? So we claim that its derivative, f prime, will be what? Will be given by what? Will be given by y prime equal to f prime of x equal to 4x to the power 3 minus 6x to the power 2. And we said that when we differentiate the constant, we get 0. So we get something like this. Okay. So far you've been looking at, the first derivative. When we look at the previous, episode, we've been looking at the first derivative of functions. Okay. All right. And we claim that the derivative function f prime can also be differentiated. Okay. So that's what today we are looking at. We are looking at a situation where after having found the first derivative, we can go further to find its derivative. Okay. So we claim that the derivative function can also be differentiated. Now, we can think of the derivative f prime as the rate of change of the slope of the tangent lines of the function f. So we explained all of this in the previous videos. And we also said that it can also be regarded as the rate at which, f prime of x is changing. Okay, let me say that again. Is the rate at which f prime of x is changing. Okay, so let's take note. I believe that understanding this would enable you to be able to appreciate all that we'll be tackling today. So we use the notation f. So let's go something here. So we use the notation f prime prime for derivative for the derivative f prime all to the power prime, not power per se, but prime, f prime prime. So f prime prime. Okay. Good. So let's take notes. So in that case, if that's the case, then it means that my f prime prime, which we can also call it the second derivative, okay? So f prime prime can also be called the second derivative, okay? Can also be denoted or be written as what? As the d of the function or the first derivative, okay? The change in the first derivative with respect to change in x, okay? So that's how we say this. And that, let me also say that, so we say that we call f prime prime the second. So let's take note. So the f prime is called the second derivative. So I want us to take note. The second derivative of f. Okay, so let's take note. So the second derivative of f. So I want us to take note. So for example, so let's cut some example. Let's cut some few examples. So example, if I give you something like this and I ask you to find f prime prime of x, what then becomes the result? So for us to find the f prime prime, or what we call the second derivative of f, what happens is that first we have to find the first derivative, okay? So the first thing is to find the first derivative. So with the first derivative, that becomes your y prime or your f prime of x. And that gives us what? So we drop the power, okay, which will become 3. Then reduce the power by 1, which gives us what? X to the power 2. And we claim that the derivative of the constant is 0. Now this is the first derivative, okay? Now the second derivative, that becomes what? Y prime prime, or what you call the f prime prime. And that gives us what? 6x. So the second derivative, okay, so the second derivative of the main function now becomes what? 6x. I hope we are okay. All right. Now, so we claim that, I want us to make this claim. Now, we claim that for higher derivatives, okay, so for higher, I will write that for higher derivative, we use the notation express, okay? So we use the notation f of n to the power f to the power n, not as in power, just like the way we can say, let's say 2 to the power 2. But it's just to denote the n derivative, okay? It's to express, this is to express the m derivative, okay? I want us to take note. It's not just power, but it's just to express the m derivative of f, okay? So I want us to take note. So anytime you see something as this, we are trying to express the m derivative of the function f. So I would want us to sort of, take note. We are okay. Very good. So for instance, if I also give you a function as this, so if I give it a function, let's say f of x equal to, let's say x to the power 5 minus 3x to the power 2 plus 1, and I ask you to find, then I ask you to find f, if I ask you to find the fourth derivative, okay? So this means that this one we call the fourth derivative. Is that okay? So if I ask you to find this, it just means that I'm asking you basically what I'm trying to do is to ask you to find the fourth derivative of the given function. So for us to find the fourth derivative, so we have to the first thing to do is to find the first derivative, then we'll go for that, find the second derivative, third derivative, before we'll be able to, find the fourth derivative of the given function. So the first thing to do is to find f prime, okay? So the first thing, so f prime of x would then becomes what? 5x to the power 4 minus what? 6x. Good. Now what then becomes, so this becomes your first derivative, okay? So this is your first, so we call this one the first, and then f prime of x becomes what? So we drop then decrease the power by 1. That gives us what? 20x to the power 3, 6. And this one we call what? The second what? We call this one the second derivative, okay? So let's take note. Then what then becomes our third derivative of the f prime. And that gives us what? That gives us what? 60x to the power 2. Remember we said the derivative of a constant is 0. So this is what we call the third derivative. Now, what then becomes our fourth derivative? So this can also be written as, just for us to be consistent, we can use this, okay? This one we can also, just for us to be consistent, we can also use this, okay? Then what then becomes our fourth derivative? So our fourth derivative becomes what? 120x, okay? So this is our fourth, so this becomes our fourth derivative. At this point, if you have any questions, please again, put it in the comment section and I would attend to you guys. Now, there's a mathematician by the name Leibniz. Leibniz came with a notation, okay? The name of the math, when we look at our previous video, we talked about Leibniz notation, okay? The last time we talked about the Leibniz notation. And we said that with Leibniz, he came out with the notation for the second derivative of the function, which is, so for instance, if I give you y equal to f of x, then we claim that the second derivative, okay? So we claim that the second derivative will just be what? Will just be something as this. I will explain it as we move on. Okay, so this one we read it as the second derivative with respect to x. Okay, note that the tools in this notation are not exponents. I want you to note that the tools in this notation is not exponents. So let's take note. It's not exponents. So please, let's take note. Let me make sure that my notation is right. It's just a notation, not exponents. I want us to take note. It's just to denote that is the second derivative. So please, let's take note. So let's get some basic examples here. So examples. So if I give you, if y equal to x to the power 5 minus 3x to the power 4 plus x, then what is your dy dx? What then becomes your dy dx? What then becomes changing y with respect to changing x? So as we mentioned by the rules of derivatives, so we drop the power, okay? Then we decrease the power by 1, and we have something like this. The one that becomes the second derivative. So with the second derivative, we use this notation to, represent the second derivative. And the second derivative becomes what? So with the second derivative means that we're just going to differentiate the first derivatives, okay? So the second derivative just means we're just going to use the first derivative, okay? So by using that, we're going to have what? 20 x to the power 3 minus what? 36x squared. Is that okay? What then becomes our third derivative? Our third derivative becomes what? So with our third derivative, you're going to use the second derivative. Okay, we're going to differentiate the second derivative. And by differentiating our second derivative, you're going to have what? 60x to the power 2 minus what? 72 what? X. What then becomes our fourth derivative? So our fourth derivative, we're going to have what? We're going to have 120x minus what? 70. Now, who can give us our fifth derivative? So you can put it in the comment section, then I would attend to you. Our fifth derivative should be what? 120. Good student. So I believe at this point, everybody understands this section. It's very interesting, It's very interesting. So If you have any questions, please put in the comment section. And at this point, I also want to mention that if you have not subscribed to my channel, please subscribe, share the content to your colleagues, to your loved ones, and let's continue to make mathematics as easy as it should be. All right, so let's look at this also nice example also. Suppose I give you y equal to 1 over x, and I ask you to find the second derivative. What then becomes the result? Now, the easiest way for us to solve this is to first try to write the main function as this, okay? So when you write it like as this, it's easier to solve it. Now, what then becomes our first derivative? So by definition, our first derivative will just be what? So we drop the power, so that becomes -1. Then we reduce the power by 1, that becomes -2, okay? What then becomes our second derivative? So by the notation, our second derivative would then be what? So we drop the power, you multiply the power by the constant that's attached to the main function. Then we do what? We decrease the power by 1. So in that case, we're going to have 2x to the power -3, or 2 to the power x to the power cube. Is that okay? So this is how we solve this problem. What if now let's look at a situation where maybe I give you something challenging. Like what if I give you something as this? Let's see whether we can look at it from a different angle. So what if I give you something as maybe if I asked for y equal to maybe 3x squared plus 1 all to the power 2, and I ask you to find the second derivative. Okay, find a second derivative. So of the main function, what do you do in a question like this? How do we solve it? How do we solve a problem like this? So the first thing to do is find the first derivative, okay? So by finding the first derivative, so that becomes changing y with respect to changing x, and that gives us what? So this is the extended, this rule. So the rule for us to solve this problem has to do with the extended power rule. And with the extended power, we said that drop the power, okay? So we drop the power, then we maintain what is under the power, then you subtract, we decrease the power by 1, so that will give us, that will remain -1, okay? That would remain 1. Then we differentiate what is inside, then we differentiate what is under the power, then we differentiate what was under the power. So that's what we said the last time. So in that case, we're going to have, so when we differentiate this, we're going to have 6x. So 6x, so that we are going to have something as this. We're going to have 6x. But when we expand this and simplify, we should have 36. That should give us what? 36x to the power 3 plus 12x, right? Then what then becomes, if that's the case, what then becomes our second derivative of the function? So that gives us what? That should give us what? 180x to the power 2. We get this one. That's good. Now let me challenge you a bit. What if I give you a problem as this to solve? So I would say try this one. If I ask you to try this problem, how do we tackle this? So I ask you to find the fourth derivative of 1 over x to the power 2. So you can pause the video, then you try it.